Alright, so today we're doing related rates, and related rates is basically it jumps off of implicit differentiation. So in related rates, you're going to deal with a lot of dx dt, dy dt, ds dt. It's essentially derivative in terms of a variable. So let's say we're finding derivative of xy plus y squared equals 100 using related rates. We're going to have 2x dx dt plus 2y dy dt, and that would be equal to 0. And based on what the question's asking, sometimes we're going to have to find out dx dt, and we're going to be given these variables. And also sometimes we're going to have to find out, dy dt of, let's say, a shape that's growing in size or decreasing in size and stuff like that. Alright, so let's start with number 1. So number 1 is if v is the volume of a cube with the edge length x, and the cube expands as time passes, find dv dt in terms of dx dt. So essentially the most important part with these questions is to visualize it or know how to write it down. So first let's start with the cube. So we're basically given the volume of a cube. That's like the basis of this question. So we know the volume of a cube is x to the cube power. So we would have x3. That is going to be our starting equation here. V equals x cubed. And we have x as the cube expands as time passes. Find dv dt in terms of dx dt. So our, let's write it down here. So v and then dv dt. X is our length, and then dx dt is how fast the length is growing or decreasing. So v, if we find derivative of v equals x cubed, we're going to have dv dt. Essentially, if you find derivative of v, it's going to be 1 times dv dt, but you don't need to write the 1. And then on the right side, we're going to have 3x squared dx dt. So essentially, this would actually be your final answer for A, but basically this means that if, let's say, we're given how fast the cube length expands, we're able to plug that in and then figure out how fast the volume is going to expand in relation. And that is exactly what we're going to do in B. So B is if the length of the cube is increasing at a rate of 4 centimeters per second, how fast is the volume of the cube increasing when the edge is 15 centimeters? So let's write down our variables. That's a really important thing to do with the related rates. Just write it all down. So first, V, the volume here, we could actually calculate it. So we know we have to find out when the edge is at 15 centimeters and the edge is increasing at 4 centimeters per second, what is the volume increasing by? So X is going to be 15 because that's the edge length. The rate at which the edge is increasing is dx dt, which is going to be 4. And we know the volume of a cube is 15 to the x cubed, which 15 cubed. But in this question, we're actually not going to use the volume, but we can just write it down. And dv dt, we don't know that. That's our unknown. So let's take this derivative function here and write it down. dv dt equals 3x squared dx dt. Now all we need to do is just plug it in and find out what this dv dt means. So we plug in 15 for x and then 4 for dx dt. We would have 315 squared multiplied by 4. And if we simplify all that, you could put it in the calculator. That would give you 2,700 and then centimeters cubed per second because it's a cube of volume, and per second. And that would be your dv dt. That would be how fast the volume is increasing given that the edge is increasing 4 centimeters per second at the edge length of 15. So as long as you can set it up, that's the most important part. Then finding the variable that you need should be pretty easy. So number 2 is essentially the same thing for A. If A is increasing, is the area of a circle with the radius r, and the circle expands as time passes, find dA dt in terms of dr dt. So this is essentially the same thing. So our area of a circle, if you remember, it's A is pi r squared. So now all we need to do is find the derivative of this. The derivative of A in terms of dA dt is going to be 1 dA dt, or we could just write dA dt. And then on the right side, we're going to have pi 2r. That is the derivative, and multiplied by dr dt. And essentially, that's your final answer for number A, or letter A actually. But that is it in terms of dr dt. And now B is, suppose oil spills from a ruptured tanker and spreads into a circular pattern. If the radius of the oil spills increase at a constant rate of 2 meters per second, how fast is the area of the spill increasing when the radius is 30 meters? So again, let's write out what we know and what we don't know. So that's the area and then the radius and how fast the radius is increasing. So first, let's look at the radius. When the radius is 30 meters, so we just write that down. That's known information. And the area, with the radius, we can calculate the area even though we're not given it. It would be 30 squared pi, which is 900 pi. And we might not use our area, but it's just good to write it down. And we're told that the radius is increasing at a constant rate of 2 meters per second. So that means dr dt is going to be 2. So if we rewrite that question here, dA dt is equal to pi 2r dr dt. And by the question, we don't know what dA dt is. That's what we're figuring out here. So if we plug in everything we know, we're going to get dA dt is equal to pi 2 and then radius is 30 times dr dt, which is 2. And if you simplify that, that would give you 120 pi is dA dt, which essentially means that given the values of how fast it's increasing and when it's increasing, the area of the circle is going to be increasing at 120 pi per second. So that would be your final answer, 120 pi. Alright, so let's take a look at these few questions. So number 17 is 2 cars start moving from the same point. One travels south at 60 miles per hour, and the other travels west at 25 miles per hour. At which rate is the distance between the cars increasing 2 hours later? So let's try to visualize what we're trying to figure out here. We're not dealing with the area, that's all we know. So we know that one car is traveling 25 miles per hour east, and then the other one is traveling 60 miles per hour south. So if we could kind of, visualize it, connect the points, we can see this is a triangle. It's a right triangle. So what are we actually trying to find out here? So we want to find out the rate at which this hypotenuse is increasing at 2 hours. So since we're not finding out the area, what equation do we actually use? So we use the hypotenuse, the equation to get a hypotenuse, which would be a squared plus b squared equals c squared. So let's just say 25, this is A, and then this is B, the direction south. So let's actually write out what we know. So we need to know dA, or A, and then dA dt, and B, and dB dt. And let's also write down C and dC dt. So let's write down what we know. So we know A is equal to we're basing this all off of at the 2 hour mark. So A at the 2 hour mark is gonna be 25 times 2, that's 50. dA dt, we're given that that's 25 miles per hour. B is going to be equal to 120 because 60 times 20. And then dB dt is 60. And now C is, we have to figure that out using the hypotenuse formula. So we're going to have 60 squared plus 25 squared is equal to, so on down here we would have 3600 plus 25 squared is 625, which is going to be equal to 4250, I believe. And the derivative, or not the derivative, the square root of 4250 is going to be approximately 65.2. So it's 65.192, but we could round up. So we know C is equal to 65.2, and a lot of times, sometimes you could actually leave it as radical 4250 if you're not allowed to use a calculator during a test. So now we're trying to find dc dt at oh, never mind. This would actually be 130.4 because we're finding everything due at 2 hours. So we would multiply 65.2 times 2. So we're still trying to find dc dt. Now I'm trying to see if we have enough space here. So we find derivative of this equation right here, a squared plus b squared equals c squared. We would get 2a dA dt plus 2b dB dt equals 2c dc dt. Now comes the rather easy part, in which all we need to do is just plug it in. Plug in everything we know into this equation, and we should be left with dc dt is equal to said number. So if we plug it in, we would have 2 open parentheses a, which is 50, multiplied by dA dt, which is 25, plus 2 times b, which is going to be 120, plus dB dt, which is 60, is equal to 2 times 130.4. So we could write it right here, 260.8, and dc dt. Now, if we add up the left side, we're going to have 16,900. And then on the right side is going to be 260.8 dc dt. Now we want to get dc dt by itself, so we just divide both sides by 260.8. And we are going to be left with dc dt is equal to 64.8. So what we have deducted is that the rate at which the distance between the two cars are increasing 2 hours later is going to be 64.8 miles an hour, or you could even round it up to 65 miles per hour, and that would be your final answer. So that's basically how fast this hypotenuse is increasing at 2 hours later. Alright, so I want you guys to try number 3 and number 4. So number 3 is dealing with the square, and you want to find out dA dt, I believe so. And number 4 is dealing with the sphere, and you want to deal with the volume, so dV dt. So you could pause the video and try those out. Alright, so number 3 is each side of a square is increasing at a rate of 6 centimeters per second. At what rate is the area of the square increasing with the area of the square 16 centimeters squared? So let's first write down what we know. First, the area of a square is going to be equal to, let's say, s squared. So that's the area of a square, and let's write down the variables we know. So a, and then dA dt, and s, and ds dt. So do we know the area? The area of the square 16. So when the area of the square is 16, we want to find out the rate at which the area of the square is increasing. So we don't know this. We need to find out dA dt. Do we know s? So we can actually figure out S from A. So if we plug in A for 16 here, uh, S would be 4. The square root of 16 is 4, so S is 4. And ds dt, we're actually given that in the problems, which is 6. And all we need to do now is just find the derivative. So we find the derivative, we're going to have dA dt is equal to 2s ds dt. So we're trying to find out dA dt, so all we need to do is just plug it in here. So we plug in 4 for s and 6 for ds dt. We're going to have 2 times 4 times 6. 24 times 2 is 48. So the rate at which the area of the square is increasing is going to be 48 centimeters squared per second at the area of 16 centimeters squared. That is your final answer. And number 4 is the radius of a sphere is increasing at a rate of 4 millimeters per second. How fast is the volume increasing when the diameter is 80 meters? Or millimeters rather. So for this, let's do the same thing. So the volume of a sphere is going to be 4/3 pi r cubed. So now what we have to do is same thing. We just write down what we know and what we don't know. So v and then dv dt, and we're dealing with diameter here, but we could just divide it by 2 and then write it as the radius. Just because the original equation has the radius, we don't want to make it any more complicated than it needs to be. So we have r and then dr dt. So are we given the volume here? How fast the volume increasing when the diameter is 80? So if the diameter is 80, we know that the radius is 40 millimeters. And the radius of the sphere is increasing at 4. So we know dr dt is 4. So let's actually find the volume here, and dv dt is what we don't know. That's what we want to figure out. So if we plug in 40 in this, we're going to have 4/3 pi 40 to the third power. And if you calculate that, you will get 64,000 multiplied by 4 divided by 3, which is going to be, or you can actually write in fraction. I don't want to write a really long decimal. So we're going to have that the volume is equal to 256,000 pi divided by 3. So that's going to be our volume. However, actually our volume isn't necessary here, but again, like always, I do like writing it out just, for so we know exactly what's happening in the question. But again, let's find the derivative of this so that we can plug in all the juicy numbers and get dv dt. So if you find derivative of that, derivative of v is dv dt is equal to, we want to move the 3 to the front. We're going to have 4 pi r squared dr dt. And now all we need to do is just plug in r and plug in dr dt. So if we plug in r and dr dt, we're going to have 4 pi r squared, which is going to be 40 squared, which is 1600, multiplied by dr dt, which is 4. And if we add all that together, we know this is 6400. And 6400 times 4 is 25,600. So we get 25,600 pi. And that is our dv dt. So essentially, and this is also 25,600 pi millimeters cubed per second because it's the volume. So we have it cubed. But essentially, 25,600 pi is at which the volume is increasing when the diameter of the sphere is 80 millimeters, or the radius is 40 millimeters. But essentially, this would be your final answer for number 4. Alright, so I want you guys to try number 6 and number 7. So number 6 is dealing with the rectangle here, and we're dealing with some area. And number 7 is dealing with the cylindrical tank, and this is going to be dealing with volume. So you can pause the video and try those out. Alright, so let's take a look at number 6. Number 6 is the length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? So what we got to do for this is we're actually dealing with 3 variables here, so it's a little bit different. But so we know the area of a rectangle is going to be length times width. And we know the length is 8, and then the width is, oh no, the length is 20, the width is 10. So let's write down what we know. So let's write down L over here, dl dt, and we have W over here, dw dt, and then area over here, and then dA dt. So what are we trying to find out here? We're trying to find out how fast is the area. So dA dt is our unknown, that's what we want to find out. And we know that the length increasing at a rate of 8 centimeters per second, so we know dl dt is 8. We know dw dt is 3. And we know L is 20, and then the width is 10. So 20 and 10. And based on that, we can actually find out the area, which is length times width. 20 times 10 is going to be 200. And now we have to, in order to find dA dt, we have to find the derivative of area is equal to length times width. So for that, we actually have to use the product rule, which is going to be f prime plus g plus, or f prime g plus fg prime. And you could also write the product rule as fg prime plus f prime g. Now, since you're adding them, it actually doesn't matter what order you put them. Some videos I do it this way, some videos I do it this way, but just know it's the same thing. So if we actually find the derivative like that, we're going to get, on the left side, we get dA dt, that's the derivative A. On this side, this is going to be f, and this is going to be g for our case here. So we get f prime, which is going to be dl dt. So dl dt is multiplied by g, which is just going to be w. And that's going to be added to f, which is going to be L times g prime, which is going to be dw dt. And all we need to do now is literally just plug it in. So we get dA dt is equal to dL dt, which is 8. 8 times 10 plus 20 times dw dt, which is 3. And we get 80 plus 60, which is going to be 140. So dA dt, which is our what we're looking for, is going to be 140 centimeters cubed per second. And that is how fast the area of the rectangle is increasing when the area is equal to 200, or rather when the length is equal to 10 and the width is equal to, or length is equal to 20 and the width is equal to 10 centimeters. And that would be final answer for number 6. And for number 7 is we're dealing with this cylinder, basically just a cylinder, that's the shape. And we're dealing with volume here, so the radius is 5 meters and it is being filled with water at a rate of 3 meters cubed per minute. This means that the volume is increasing at 3 meters cubed per minute. How fast is the height of the water increasing? So we're going to be looking for height here, or rather dHdt. So let's write it out. So we know that the volume of a cylinder is V equals pi r squared h. And let's write down all the variables we know. So we know our dr dt, And we're going to be dealing with H here. We want to find out dH dt. So dH dt is our unknown here. We don't need to know the volume, but I'll just write down dV dt is what we are given as well. So these are all the variables we're going to be dealing with here. It's total 6. We know 5 of them, or we can figure out 5 of them. We need to figure out the last one. So we know the tank has a radius of 5. So we're given 5, and it is being filled with the water at a rate of 3 meters per 3 meters cubed per minute. So dV dt is going to be 3. How fast is the height of the water increasing? So for the height, we're not actually given any information about the height. So uh, but you're gonna see here, we don't actually need to know the height. And since we don't know the height, we also don't know the volume. But we don't need to know the height or the volume here. But let's just keep it here just so you guys can visualize it. And for dr dt, we don't see any information about the radius increasing or changing at all. So we just say dr dt is 0 because we're not given information about it, so we have to assume it. So let's find the derivative of V equals, or rather the cylinder volume formula. So if you define derivative, we get dV dt is equal to, so we're actually going to have to use a product rule for the right side. So we have pi r squared times h. The product rule is f prime g plus fg prime. And we know that for example, g prime is going to be dh dt, and then g is going to be or h rather. So if we use the product rule right now and just end up with some stuff, and then we'll figure it out. F prime is going to be the derivative of pi r squared, which is going to be 2r pi, or 2 pi r rather, which is also a circumference, multiplied by g, which is going to be h. And now we're going to have, on this side, we're going to have, oh, actually, we have a dr dt as well. Dr dt 2 pi r times h. And then on the right side, we're going to have f, which is going to be pi r squared, multiplied by the derivative of h, which is going to be dh dt, which is what we don't know. Now we're left with this, kind of long equation. Let's start plugging in stuff we know. So we know dV dt is equal to 3. dr dt, do we know it? dr dt is 0. And multiplied by 2, multiplied by r, which is 5, and pi, multiplied by h, plus pi r squared. If we plug in 5, that's going to be 5 squared, which is 25 pi. Oh, I wrote 2 pi, but 25 pi multiplied by dh dt. So you see here we're left with an h, but we don't know what it is. But this is why we actually don't need to know the h value. So dr dt, we know that's 0, and 0 times everything here becomes 0. So the h, the r value, since we don't know h, it becomes irrelevant anyway. So all of this goes away, doesn't matter in the equation anymore. So we're left with 3 is equal to 25 pi dh dt. Now we want to get dh dt by itself, so we just divide 25 pi on both sides. 25 pi. 25 pi, and we're ended up with answer dh dt is going to be 3 over 25 pi, and the units of this is going to be meters per minute, because it's magnitude on the first dimension. So 3 over 25 pi meters per minute would be your final answer, which is going to be essentially dh dt, which means how fast the height of the water is increasing in the cylindrical tank when the rate of the water is 3 meters cubed per minute. And that would be our answer for number 7. Alright, so that was basically related rates, and related rates does get a little bit complicated at times, but the basic premise of it is if you can figure out what you're looking for in the question, like what you're answering for, whether it's the HDT, you're trying to figure out how fast the height of something is increasing or something. If you can visualize what you're trying to figure out and the formula for it, then finding the derivative and the answer to it will be super easy. But the main thing is understanding the question and how to set up the formula that you're gonna need to answer for. And yeah, it's basically for related rates. You're gonna be dealing with a lot of dx dt, dy dt. It's basically just a derivative of a variable in terms of that. And yeah, it's basically it.